Heisenberg Uncertainty Principle. In Chinese, this is called 测不准，海森堡测不准原理。Okay, so it has two versions. First version, second version. First version involving the position and the momentum. Second version involving time and the energy of the photon. So both of them is larger than equal approximately h divided by the 2 pi, which is also defined as h bar. H bar is, they write it like that. So like a h, and then you have a prime. So this is called h bar. And this number, according to the Planck's constant, which is 6.63 divided by 6.28 times 10 to the negative 34. So it's equal to 1.055 times 10 to the negative 34. So that's the h bar. So this is also the same. It's larger than that. So what does that mean? It means that the uncertainty in the position, if you want that one to be large, then this one can be small. Or you can say, if you want this one to be small, then you have to pay the price of having this one to be large. Similarly, if you want to measure the time more accurately, then you must give up the accuracy that you can get in the energy. So E is the energy. And this is the momentum in the x direction. Okay, momentum. All right, let's say if you want to measure like something's position, right? So in order to see that, you need to shine a light on it. Shine a light on it, okay? And you want to see the position of this guy, right? Now, when you want to do that, this light has a wavelength, and that wavelength is lambda, right? So if you have a wavelength of lambda and you want to know the position using this photon, right? So this is belong to a photon. Then the delta x, by using this light, the best you can measure, because this one's changing, and from here to here is lambda. So according to the measurement expert, this the best that you can get in terms of accuracy, right? Or the uncertainty that you're going to have, at least it's going to be at least about lambda this much. Now, the momentum is equal to E, the energy of photon, right? The momentum of a photon, right? This is the momentum of a photon. It's energy divided by speed of light, right? And this one here is equal to h, the Planck's constant, times the frequency of the photon. And this one here is lambda, right, times f, right? So light speed is equal to wavelength times frequency. So then this can cancel. So that's equal to h divided by lambda. So you can see that the delta x is equal to lambda. And then here is a lambda. So the best you can find this p, or the uncertainty in the p, using this this photon with lambda, right? It's the best you can find. It's going to be h over lambda also. So when you hit this this object with your photon, this photon will try to transfer its momentum to it. And I mean, the most you can transfer is the momentum itself, right? So the uncertainty that you're going to have in this measurement is going to be about h over lambda. Right? It can be smaller, but you know, it's something about that range. So now if you add these two together, or you time these two together, which is delta x times delta px, then you get lambda times h over lambda. So that's equal to h roughly, right? Well, this you don't need. Now, if you will go through this with a more mathematical derivation, you will find that this delta x times the delta px, it is actually larger than and equal to not just the h, but it actually can do a little better, which is h divided by this 2 pi, right? Or you can say, well, you don't need that. It's equal to h bar, h and then with, right, like that, okay, h bar. So that's your the discussion leading to this results, and this results, it's called Heisenberg's, let me change the color here, Heisenberg's uncertainty principle. Okay. Now you can do the similar argument about the second version. So delta t times the delta E is larger than and equal to this h divided by 2 pi, h bar, which is equal to h bar divided by h bar itself. Okay. So let's give an example. All right. Let's say you can measure an object, and you know the object speed is equal to v, and that's equal to say 10 to the 6 meter per second. Okay. And now, given that, what is the delta x that you can get, right? The uncertainty of the position of this object. This object is moving at 10 to the 6 meter per second. And according to Heisenberg's uncertainty principle, what is the best you can get in terms of position for this object? So then you can then say for delta p x in the x direction, so same direction, right? So before that, you have p x is equal to m times v, okay? And let's say this is an electron you're talking about here, right? So that way you know your mass, which is 9.11 times 10 to the minus 31 kilogram, and then let's say the accuracy of this v is plus minus 0.1%. Okay, that's the best you can get, right? So then this is 10 to the 6, right? But you have this plus minus 0.1%. Okay, so what is this? So that's equal to 9.11 times 10 to the negative 25, right? So when you have this plus minus 0.1%, which basically the 0.1% here is equal to 10 to the negative 3, right? So then this one here, the uncertainty of this guy is 9.11 times 10 to the negative 28, okay? Now, according to Heisenberg, right? Heisenberg, right? If I can spell that. Heisenberg principle, uncertainty principle, right? That delta px times delta x is equal to h bar. So then you can then say delta x will be, well, this is larger than, right? So we're going to put an equal first. It's going to be larger than, but that's h bar divided by this guy here. So that's 9.11 times 10 to the negative 28. And you this one here is 1.055 times 10 to the negative 34, and then divide by that number there. Okay. So that's equal to, this is about 10, it's negative 35. So that's come out to be 10 to the negative 5. And this is 10, that's 9. So it's about 1 point something, right? So let's say 1.1 times that. So that's in meter. So that's the delta X. So that's the accuracy or the uncertainty that you can get of the position of electron in this example. Okay, so I'm going to stop there. And what we have reviewed is Heisenberg Uncertainty Principle. And there are two versions of it. And let's repeat it. So delta P X, delta X is larger than and equal to H bar, right? And the other version is delta E, the energy of photon, times delta T is larger than equal to H bar, okay? And this number is equal to 1.055 times 10 to the negative 34. The unit is joule times second. As you can see, this is joule and this is second. And this is MV. And this one here is basically V times delta T, right? And this unit here, the MV square is joule, and this delta T is second. Okay, so the joule second, it's indeed okay. All right, so we're going to stop there. Keep watching. Keep learning physics.